You ever wonder how we really know what holds molecules together, or what gives them all their unique and sometimes weird properties? Well, it turns out we're not just guessing. There's a kind of quantum blueprint that lets us predict the physical world with incredible accuracy. And today, we're going to learn how to read it.
And to see just how powerful this blueprint really is, we are going to tackle a very specific, and frankly, a very cool mystery. Why on earth does liquid oxygen, which pretty much just looks like pale blue water, get grabbed, pulled, and even levitated by a strong magnet? I mean, the simpler models in chemistry, they have no answer for this. None. The answer isn't some kind of magic trick. It's pure quantum mechanics. And to solve this puzzle, we have to dive into something called molecular orbital theory. It's the language that this quantum blueprint is written in.
All right, first things first. Before we can build anything, we need to get familiar with our tools. So in this first part, we'll go over the fundamental rules and the key pieces of our blueprint.
Okay, so the core idea is actually pretty simple. When two atoms get close, their individual homes for electrons, those are called atomic orbitals, they start to merge. Think of them like waves in a pond interfering with each other. And when they do, they create a brand new set of orbitals that don't belong to either atom anymore. They belong to the entire molecule. And those are the molecular orbitals you see right there in the middle.
Now, this interference can happen in a couple of ways. The first is called constructive interference. This is when the atomic orbitals overlap in a way that packs the electrons right between the two atoms. This can happen head-on, which we call a sigma bond, or side-by-side to make a pi bond. Either way, this creates a super-stable, low-energy situation called a bonding orbital. You can think of these electrons as the molecular glue that holds everything together.
But of course, there's a flip side, destructive interference. In this case, the orbitals combine in a way that actually pushes electron density away from the space between the atoms. This creates a really high-energy, unstable situation called an anti-bonding orbital, and we mark it with a little star. And just like before, you can have sigma star, or pi star anti-bonding orbitals. These guys are the opposite of glue. They actively work to push the atoms apart.
So we've got stabilizing glue, and we've got destabilizing forces. How do we know which one wins? Well, our blueprint comes with a built-in diagnostic engine. It's a really simple calculation that tells us flat out if a molecule is going to be stable or not.
And here it is, the bond order formula. It's just 1/2 of the number of electrons in those glue orbitals minus the number of electrons in the anti-glue orbitals. The number you get is amazing. It predicts real-world stuff, stability, how strong the bond is, and yeah, as we're about to see, even things like magnetism.
A blueprint is totally useless if it doesn't work in the real world, right? So let's test drive our new diagnostic engine on the two simplest molecules you can possibly imagine, hydrogen and helium.
Let's start with a hydrogen molecule, H2. Each H atom has one electron. When they combine, both of those electrons can drop down into that comfy, low-energy sigma bonding orbital. So what do we have? We've got 2 bonding electrons and 0 anti-bonding electrons. We plug that into our formula. 1/2 of 2 minus 0, that equals 1. A bond order of 1 predicts a stable, single bond. And that's exactly what hydrogen has in real life. The blueprint works.
Okay, that was a success. Our blueprint nailed it for hydrogen. So what happens if we move to the next element on the periodic table? Helium. What does the blueprint predict for a hypothetical He2 molecule? This picture really tells the whole story. A helium atom has 2 electrons, so 2 of them together have 4. The first 2 fill up that nice, stable sigma bonding orbital, just like in hydrogen. But the next 2, they've got nowhere else to go but up, into that high-energy, destabilizing sigma star antibonding orbital. So our math is 1/2 of 2 bonding minus 2 antibonding, which equals a big fat 0. A bond order of 0 means there's absolutely no advantage to forming a bond. The stability is perfectly canceled out by the instability, and that's precisely why the He2 molecule just doesn't exist. Our blueprint is 2 for 2.
We've got our tools. We've confirmed our blueprint works on the simple stuff. Now it's time. Let's tackle that grand challenge we started with and finally unlock the secret of oxygen's bizarre magnetism.
So as we move to bigger atoms like oxygen, we have more orbitals to deal with. Now, the exact energy levels can sometimes shift around a bit, but for oxygen and fluorine, they follow this very specific, straightforward order you see right here, and this exact arrangement is the key to solving the entire mystery.
And here it is. The big reveal. We take the 12 valence electrons from 2 oxygen atoms. We start filling up our energy diagram from the bottom. After we filled all the lower orbitals, we've got 2 electrons left over.
They have to go into the pi-star anti-bonding orbitals. Now, here's a crucial quantum rule. Electrons would rather occupy separate orbitals before they're forced to pair up. And the result? O2 has 2 unpaired electrons, sitting all by themselves. Oh, and the blueprint also predicts its bond order, 1/2 of 8 bonding minus 4 antibonding equals 2. A stable double bond, just like we know it has.
So what's the big deal with these unpaired electrons? Well, having them means the molecule is paramagnetic. It's just a fancy word for a type of magnetism where a substance is attracted to an external magnetic field. This property, predicted perfectly by our blueprint but totally invisible to other theories, this is why a magnet can grab and levitate liquid oxygen. The mystery is solved.
So the blueprint totally cracked the oxygen case, but its predictive power goes so much further. It's like having a master dashboard for understanding the very nature of chemical bonds themselves.
I mean, just look at this graph. It shows the blueprint in action, plain as day. Along the bottom, you have the bond order we calculate. And on the sides, you have real-world measured data for bond energy and bond length. The trend is just undeniable. As the bond order goes up from 1 to 2 to 3, the bond energy, how strong the bond is, goes right up with it. At the same time, the bond length, the distance between the atoms, gets shorter and tighter. The theory's predictions line up perfectly with what we can actually measure.
So, we can pretty much boil all this down to 3 fundamental laws. First, the stability law. You have to have more glue electrons than anti-glue electrons or the molecule just won't form. Simple. Second, the energy and length proportionality law. A higher bond order means a stronger bond and a shorter bond. And finally, the quantum truth. The way electrons fill these orbitals dictates everything, including really cool properties like magnetism.
So what's the big takeaway from all this? Molecular orbital theory isn't just some abstract model to describe stuff we already know. No, it's a powerful predictive engine. It is the blueprint that translates the strange, invisible rules of the quantum world into the tangible, physical reality that we see all around us. And that just leaves one question, right? Now that we know how to read it, what else can we predict?